All right, we're going to go ahead and jump into chapter 14. Again, this is taken from Zumdahl Chemistry, talking about acids and bases. And so we want to take a few moments and begin this unit with some basic definitions and a couple of ideas of what we're going to deal with. First off, our learning goal for this section is going to be, one, the definitions of models of acids and bases, and two, how acid strength relates to equilibrium. We're going to be using this some basic background knowledge. And so we actually should be able to run through this part fairly quickly. Now, we have three main models that we're going to use in order to discuss acids and bases. The first, Arrhenius, which we've dealt with before, which says that acids just produce H plus ions in solution and bases OH minus. And then we have Brønsted-Lowry, which say acids are proton donors and bases are proton acceptors. This is where we're going to bring in our acid and our base. In this case, we'll use water a lot as our base because of its amphoteric properties. And in the end, we're going to actually form what are called our conjugate acid and conjugate base.
The Brønsted-Lowry concept defines acids as proton donors and bases as proton acceptors. In the reaction of aqueous hydronium ions and ammonia molecules, the hydronium ion acts as the Brønsted-Lowry acid and the ammonia molecule as the Brønsted-Lowry base. The net effect is that of a proton transfer from hydronium to ammonia, forming water and the ammonium ion.
So as you're able to see, it's just about the transition of the electron from one form to another, forming, therefore, a conjugate acid and conjugate base pair, which we talked about earlier in the year. Now, when we put a acid in water, one of the things that we'd expect to happen is that it's going to dissociate depending on its strength, whether it's a strong electrolyte or weak electrolyte. In this case, we have our acid, which is going to be represented by HA, plus water being our base in this case. At equilibrium, it's going to form our conjugate acid, which is a hydronium ion, plus the conjugate base, which is whatever the remaining part of the salt or from the acid would be. It's everything after the hydrogen that's been released. And so you see sort of a picture of what's actually going on. Now, the conjugate acid is formed when the proton is transferred to the base. So once we lose that proton, we now have this thing that is positively charged, and that is our quote-unquote conjugate acid. Now, strong acid, we know this from before. Strong acid is going to dissociate basically immediately in water, and so its ionization equilibrium actually lies far to the right, meaning we're looking at mostly the products. Now, it's going to yield a weak conjugate base, whereas a weak acid, ionization equilibrium lies far to the left, or meaning it's going to dissociate very little, and it's actually going to have a stronger conjugate base. Here's a couple of examples of what we're talking about. So, if I have a strong acid, HA, in my reaction, I'm expecting that almost all of it will begin to break down, whereas there'll be very little in the case of a weak acid, where only a few particles, and how it's usually termed as less than 5%, will actually dissociate in water. Now, here are some relationships that we want to keep in mind. If our Ka value is very large, that means that we're dealing with a strong acid, versus if it's very small, it's going to be a weak acid. Here are a couple other things that you just want to keep in mind. You can take a moment and pause the video and then come back to it at another point. Now, as I said before, water is amphoteric, which just means it can act as an acid or a base. Now, because of this, we actually have what's called the dissociation constant of water. And it's a concentration of H plus ions times the concentration of hydroxide ions, just like we would have before. And this answer always comes out to 1.0 times 10 to the negative 14, no matter what solution it contains, no matter where you find it at 25 degrees, the Kw, or the dissociation constant of water, should be 1 times 10 to the negative 14. Now, a couple of situations, and I believe some of these are very self-explanatory, so I'll brush over them very quickly. If I have a concentration of hydrogen ions that is equal to that of hydroxide ions, I'm dealing with a neutral solution. Whereas I have more hydrogen ions than hydroxide ions, I have an acidic solution, and vice versa. More hydroxide, then I'd have a basic solution that I'm using. Now, a quick concept check. Using our information, using our reaction up top, what is the equilibrium constant for this expression for an acid acting in water? Take a few moments, pause the video. Now, our final answer should come out to K equals our products, concentration of hydronium ion, times the concentration of our conjugate base, divided by our acid concentration. One thing you should notice is that water is missing from this situation. And why? Because water in this case is a constant, and so we don't have to calculate it in. Second concept check. If the equilibrium fires right to the left, the value for Ka you would expect to be what? Versus if it lies far to the left, what would you expect for the Ka value? It should be greater than 1 if it lies far to the right, indicating that you also have a strong acid, whereas less than 1 if we're dealing with a weak acid, or to the left. And last but not least, this is where I want to leave you for today, and we'll pick this up in class tomorrow. Consider the weak solution of sodium with its anion, where A- is the anion of the weak acid HA. Which way will the equilibrium lie? Because of the fact that we say it's a weak acid, where would you expect it to be? And this is where we'll wrap it up for now, and make sure to come to class. Hopefully, if you've taken your notes and that you're ready to go. Let me know if you have any questions. We'll continue this in class. Thank you and have a great evening.